Fracture. It can be defined as a separation of a solid body or fragmentation of a solid body into two or more parts under the application of stress is called fracture. So the fracture, it is of two types, ductile fracture and brittle fracture. Ductile and brittle fracture. So this fracture, this subject, it is very vast and it involves disciplines as diverse as solid state physics, quantum mechanics and material science. So this fracture, it is divided into two types. It is mainly of two types, that is ductile and brittle fracture. Ductile fracture, this type of fracture, it is associated with some measurable amount of plastic deformation during and prior to fracture. Whereas brittle fracture, this type of fracture, it is associated with very little plastic deformation. That means there is no measurable amount of necking or reduction in area or elongation that takes place. This brittle type of fracture, it is usually flat with no necking or very small amount, only a small amount of plastic deformation prior to fracture takes place. So this fracture, either ductile fracture or brittle fracture, it takes place in one of these following ways. The following ways are application of load, that is slow application of load, like tensile fracture. Rapid application of load, which comes under the category of impact loading, and cyclic loads or cyclic stresses, which comes under fatigue, and then time dependent deformation, that is creep, or due to environmental effects like stress corrosion cracking, hydrogen embrittlement, liquid metal embrittlement, etc., as well as internal stresses due to thermal gradients in the material because of uneven expansion and contraction that takes place. So these are the various ways in which fracture occurs. So the fracture occurs due to very slow rate of loading, under the application of slow rate of loading, due to sudden or rapid loading, that is impact, as well as cyclic loading. Cyclic stresses are due to cyclic loads, that is fatigue, due to time dependent deformation, that is creep, and due to internal stresses, that is due to uneven contraction and expansion that takes place in the material due to difference in temperatures in the material, as well as due to environmental effects, that is like stress corrosion cracking, hydrogen embrittlement, liquid metal embrittlement, etc. So fracture occurs either one of these following ways. So these are the various which leads to fracture. Fracture may take place during the slow rate of loading, sudden, cyclic loading, time dependent, or due to internal stresses, or due to the environmental effects. So the process of fracture, in most of the cases, it is divided into three categories, three types. That is, one is damage accumulation. The process of fracture, it is divided into three steps, that is damage accumulation. Next is the nucleation of cracks, or voids, and then the growth of cracks or voids, which involves the coalescence of these voids, and finally it leads to fracture. These voids coalesce, they grow into a large crack, and when the remaining structural member, it is unable to carry the load, to withstand the load, the cross-sectional area decreases to such an extent that it cannot carry further load, it fails. Okay, so the process of fracture, it is divided into, in most of the cases, it is divided into these categories. This is the process of fracture, which is divided into the various categories, and fracture can occur in any one of these following ways. So already some introduction has been given in the previous modules when dealing with fatigue, when dealing with creep, the ductile fracture or the brittle fracture. So ductile fracture, it is where some appreciable amount of plastic deformation takes place prior to and during the fracture, whereas in the case of brittle fracture, there is no plastic deformation, there is no shape change, or there is no indication that this structure or the material will undergo failure. So the fracture is catastrophic in the case of brittle fracture. So among the three categories of fracture, damage accumulation, nucleation of voids, and growth of the voids, damage accumulation, it is mostly related to the material properties like the atomic arrangement, the crystal lattice, grain boundaries, prior history of loading, etc. When the local strength or ductility is exceeded, then a crack nucleates, it propagates under the load, and then finally it leads to fracture. LEFM approach, which is known as linear elastic fracture mechanics. Linear elastic fracture mechanics. So this LEFM, it applies theories of linear elasticity to the propagation of cracks or to the fracture. Linear elastic fracture mechanics, it applies theories of linear elasticity to the fracture or to the propagation of cracks. If we define fracture toughness of a material as the resistance of a material, it is the ability of a material to resist fracture. So in the case of linear elastic fracture mechanics, it applies theories of linear elasticity. It applies theories of linear elasticity to the propagation of cracks or to the fracture. So fracture toughness, it is defined as ability of the material to resist flaws, to resist fracture in presence of flaws. Fracture toughness means it is the ability of a material to resist fracture in presence of flaws. Various standard organizations like American Society for Testing and Materials, British Standards of Institutions, Japanese Institutions of Standards. So these are the various standardization bodies which have standards for fracture toughness. So these are the various standardization bodies which have the various standards for fracture toughness, A quantitative understanding of cracks is very important, because a quantitative understanding of cracks is very important to measure the stresses at the crack tip or at the vicinity of the crack. Because if one can determine the stresses at the crack tip or at the vicinity of the crack, then one can answer the most important question, that is, what is the external load required to propagate the crack? So this is one of the important questions that can be answered if one can determine the stresses present at the crack tip or in the vicinity of the crack. So as discussed earlier, fracture is of two types. Ductile fracture and brittle fracture. So ductile fracture, for the case of very ductile materials, polycrystalline metals, like that of gold and tin, they can be drawn down to a point before rupture takes place. So this is for the case, this is a ductile fracture for the case of, this is a ductile fracture for the case of very ductile polycrystalline metals like gold, lead, which can be actually drawn down to a point before final rupture takes place. And for the case of normal ductile materials with some amount of some medium to some high amount of reduction in area, percentage elongation and necking takes place. This is for the case of moderate ductile materials which fractures in this form, that is known as cup and cone fracture. This is known as cup and cone type of fracture, which you have already seen in the case of a tension test. In the case of the tension test for the case of mild steel, where necking takes place, some localized reduction in area takes place, percentage elongation takes place, and this fracture type of fracture is known as cup and cone for the case of moderately ductile materials. And for the case of brittle materials, where the fracture surface is essentially flat, no measurable amount of plastic deformation. This is for the case of glasses and crystalline ceramics, which fracture at room temperatures normally show no evidence of plastic deformation that takes place. The fracture surface is essentially flat. So this is the type for the case of brittle fracture. And this is for the case of normal ductile materials. And this is for the case of very ductile materials which show this type of rupture before failure. And in the case of impact testing, we have discussed about the factors that contribute to brittle type of fractures. The factors that contribute to brittle type of fracture is the low temperature, high strain rates and stress concentrations that exist at the notch. So these are the three factors which contribute to brittle type of fracture. That means even a ductile material, it can fail in a brittle manner under these conditions, that is low temperature, very high strain rates of loading, impact loads, and then stress concentrations which exist at the notch. So we shall bring out some differences between brittle fracture and ductile fracture. So brittle fracture, where the fracture stress, sigma F stands for fracture stress. Fracture stress, it is less than the yield strength. Sigma Y, subscript Y, stands for yield strength. and for the case of ductile fracture, where the fracture stress is greater than yield strength. And in the case of brittle fracture, there is no necking that can be seen, that is no localized reduction in cross-sectional area, as well as reduction in area percentage elongation. So percentage elongation and reduction in area is very, very low. Whereas in the case of ductile fracture, there is some appreciable amount of necking can be seen. Necking is seen in the case of ductile fracture, and some medium to high values, we can have this medium to high values of reduction in area and percentage elongation can be seen in the case of ductile fracture. And the appearance of brittle fracture, it is shiny, granular, and it is of cleavage mode. Whereas in the case of ductile fracture, dimples can be seen in the fracture surface, which indicates microvert coalescence, and it appears dull, fibrous type of appearance. So these are some of the differences between brittle fracture and ductile fracture. So the fracture stress is less than the yield stress. In the case of brittle, there is no necking, very low percentage elongation it can be seen in the case of some brittle materials, and the appearance is shiny, granular, and cleavage mode in the case of brittle fracture. Ductile fracture, the appearance is dimples can be seen on the fracture surface, and it appears very dull and fibrous. The fracture surfaces that can be observed, that means whether it is a ductile fracture or brittle fracture, the appearance of this, it can be seen under an electron microscope, that is scanning electron microscope. So most of the fracturographic studies, they can be done using the scanning electron microscope, SEM. So to find out the appearance of fracture, the fracture surface. Now we shall discuss more detail about the brittle fracture, because this brittle fracture is a very serious consideration. Brittle fracture, the brittle fracture problem. As discussed, brittle fracture, it occurs with very, very little microscopic plastic deformation that takes place, and moreover, during this, in the case of brittle fracture, there is no change in the dimensions of the specimen, no change in the shape of the specimen. So there is no indication that the fracture is going to take place. The fracture is sudden and rapid. A very rapid crack propagation takes place, and the fracture occurs suddenly. So catastrophic failure takes place. So this brittle fracture is a very serious problem to be considered, because it leads to lot of economic loss as well as loss of lives. So this a great effort has been expended mainly to frame certain methodologies to avoid this brittle fracture. So this brittle fracture, it is to be avoided at all costs, because it leads to great economic loss and loss of life. The catastrophic nature of brittle fracture was dramatically exemplified with the failure of Liberty ships during the Second World War. After the war, G.R. Irwin and his associates in the Naval Research Laboratory, they laid for the foundation for what we call today, that is fracture mechanics. They laid the foundation for fracture mechanics. So Liberty ships, they are only one example of catastrophic failure. So these brittle failures, they are the recurring failures for aircraft, bridges, rail, wheels, as well as other heavy equipment. Although brittle fracture does not occur today with the same frequency as it did once, but still, in order to avoid this brittle fracture problem, proper design and manufacturing processes has to be adopted. In a typical scenario for brittle fracture, a small flaw it is introduced during the manufacturing process or when the component is placed in service. So this flaw, under the action of load, it grows stably and then it undergoes a rapid propagation with the stresses and finally leads to failure. When the flaw it reaches a critical size, failure occurs suddenly, approaching that of velocities, that of speed of sound. So brittle fractures, they are generally flat with very little plastic deformation, very little microscopic plastic deformation that take place. So brittle fracture, they occur in body-centered cubic materials and in HCP metals, hexagonally close packed materials, but not in the case of face-centered cubic materials, unless until there is some evidence of grain boundary embrittlement takes place. Even normal metals, they can fail in a brittle manner under the conditions of low temperature, high strain rates and stress concentrations. So this generally it is seen in the case of BCC metals, where there is a gradual transition from the case of ductile fracture to that of brittle fracture, as the temperature is lowered. That is, ductile brittle transition temperature is seen in the case of BCC metals. The factors that promote brittle fracture are: one, that is high yield strength. So the factors that promote brittle fracture, they are high yield strength, which has high elastic energy levels, high yield strength, then coarse grain size, then third, low temperatures that causes ductile brittle transition temperature in the case of BCC metals, coarse grain size which build up very high stresses due to dislocation pile-ups, high stresses that build up due to dislocation pile-ups, then very high strain rates that does not allow much time for the stress redistribution to take place, very high strain rates where the time is very less for stress redistribution to take place, coarse carbides and precipitates. Then 6, we have the deep notches which acts as stress concentrators, which locally raises the stress. So these are some of the factors that promote brittle fracture: high yield strength, which has very high elastic strain energy values; coarse grain size, which build up high stresses due to dislocation pile-up; low temperatures, that is for the case of ductile brittle transition temperature, which is seen for BCC metals; high strain rates, where the time for redistribution of stress is very low; coarse carbides and coarse precipitates that promote brittle fracture; and deep notches, which acts as stress concentrators, which locally raises the stress at the vicinity of the notch, where the stress distribution is not uniform, it is maximum at the vicinity of the notch or at the tip of the crack. So these are some of the factors that promote brittle fracture. And coming to ductile fracture. Ductile fracture is not a severe problem as the case for brittle fracture, because one can notice the changes in the shape of the component before it fails, because it undergoes some amount of plastic deformation necking is seen, some reduction area is seen, some percentage elongation is seen, and you can know that this material will finally eventually leads to failure. Whereas brittle fracture, that is very serious because it occurs without any warning. So this ductile fracture, it occurs by the nucleation of voids which takes place at the stress concentrators, at the inclusions, at the stress concentrators. Voids nucleate. These voids, they grow and coalesce to form a large crack. Then this crack, it propagates perpendicular to the plane of maximum tensile stress, and finally when the remaining cross section of the material, it decreases to such an extent it cannot bear the load, it finally leads to failure. So these are the various steps in the ductile fracture, where there is a localized reduction cross sectional area where necking takes place, which leads to triaxial state of stress at the neck. At this portion, the voids nucleate, these micro voids nucleate at the stress concentrators. Then these voids, they grow. So these voids, they coalesce to form a large crack. So these voids, they grow, coalesce to form a crack, and finally the material separates by shear. So this large crack, it grows and finally leads to failure, separation. So these are the various stages in the ductile fracture, where the reduction in area, this is the necked region, which leads to stress concentrations. Voids nucleate, they grow and they coalesce to form a large crack, where this crack propagates under the application of tensile stress in a direction perpendicular to the tensile stress and finally leads to failure. Now coming to the important topic, that is theoretical cohesive strength of metals. Metals are of greater technological value because of their very high strength combined with some amounts of plasticity. The strength is mainly due to the cohesive force between the atoms. Larger the cohesive force, it is related to greater the elastic constants, higher melting points, and small coefficients of thermal expansion. Now, this is a figure which indicates the cohesive force sigma, cohesive force between the two atoms as a function of separation between the atoms, as a function of separation between the atoms, that is x. This figure shows the variation between the cohesive force between the atoms as a function of separation between the atoms, that is x. So the distance between the atoms in the unstrained condition, it is A0. As the tensile force is applied, the separation between the atoms increases. The separation between the atoms, it increases. The repulsive force decreases. This curve is a resultant of the attractive forces and the repulsive forces between the atoms. As the tensile force is applied, the separation between the atoms increases. The repulsive force decreases more rapidly than the attraction force. And as the separation still increases further, a stage is reached or a point is reached at which the repulsive force becomes negligible and the attractive force starts to decrease. So that point is the maxima in the curve, which indicates the theoretical cohesive strength of the material. So as the separation between the atoms increases, the separation between the atoms, we have the atoms, the separation between tensile force is applied, the separation between the atoms, it increases. The repulsive force, it decreases. The repulsive force decreases as the separation increases to a certain extent that the repulsive force becomes negligible and the attraction force, it starts to decrease. So that point is maxima in the curve and is represented as the theoretical cohesive strength of the material. A good approximation to this theoretical cohesive strength can be obtained if one assumes this to be a sine curve. If this cohesive force was a separation between the atoms, if one assumes this to be a sine curve. So this can be represented as sigma is equal to sigma max sine 2 pi x by lambda. This is sine 2 pi x by lambda, where sigma x is the theoretical cohesive strength, x is equal to A minus A naught, that is the separation between the atoms, that is the displacement. Lambda is the wavelength, x is equal to A minus A naught, this is the interatomic displacement with a wavelength of lambda. This is the wavelength. For small displacements, it can be approximately written as sin x, sin is approximately equal to x. Sin x is approximately equal to x, that is for small displacements. So this equation, it can be written as sigma is equal to sigma max 2 pi x by lambda. And if we assume a brittle elastic solid, then sigma is equal to Young's modulus into strain, that is stress is equal to Young's modulus into strain. So this can be further written as sigma is equal to E into x by A naught. And substitution of this equation in this equation we have, where this is equation 1 and this is equation 2, this is 3 and 4, we have Ex by A naught is equal to sigma max 2 pi x by lambda. So eliminating x, we have sigma max is equal to E lambda by 2 pi A naught. So this equation we can write it as 4. If this is written as 3 and this as 4. So sigma max is equal to E lambda by 2 pi A naught. If we make reasonable assumption that A naught is equal to lambda by 2, we have this equation 4 further reduces to sigma max is equal to E into A naught is lambda by 2. So we have E by pi. Sigma max is equal to E by pi. Therefore, the potential exists for higher values of cohesive strength. When fracture occurs in a brittle solid, the work expended in producing a fracture results in two new surfaces. These two new surfaces has a surface energy gamma subscript s, known as the surface energy, and has the units of joules per meter square. Then the work done by these fracture surfaces in causing fracture is given by the area under the stress displacement curve. So this can be written as 0 to lambda by 2. The work done per unit area of the surface in creating fracture, it can be obtained by the area under the stress displacement curve, which is given as integral 0 to lambda by 2 sigma max sine 2 pi x by lambda into dx. So which is equal to lambda sigma max by pi. So this is equation 5. So which is equation 6. This is equation 5. Since this energy is equal to energy required to create two new crack surfaces, which has energy gamma s, so this is equal to lambda sigma max by pi, which is equal to energy required to create two new crack surfaces which has surface energy gamma s. We have lambda is equal to 2 gamma s into pi by sigma maximum. So this is equation number 7. Now substitute this equation number 7 in equation number 4. That means we are trying to eliminate lambda. So we have sigma maximum is equal to 2 gamma s by pi. Sigma max is equal to E 2 gamma s pi by 2 pi a naught into, this is sigma max square. That is, sigma max is equal to E gamma s by a naught whole to the power of 1 by 2. So this is the equation we have arrived. So this is equation number 8. So eliminating lambda, that is substituting this equation for lambda in equation 4, we have eliminated lambda, and finally we have arrived at an equation sigma max is E gamma s by a naught whole to the power of half. Experience with high strength steels shows that fracture stress in values greater than 2 GPa is exceptional. It has been found that the fracture stress, it is less than 10 to 1000 times lesser than that of the theoretical strength. That means when tested for most of the materials, the fracture strength, it has found to be 10 to 1000 times lower than the theoretical strength. So this leads to the conclusion that cracks or flaws are responsible for lower fracture strength than the theoretical value. So this is the figure which shows an infinitely wide plate which has an elliptical crack of length 2c. As we have already discussed in the case of stress concentrations, that what is the effect of a notch, what is the effect of a discontinuity or flaw? It raises the stress at its vicinity. So the stress raises to a maximum value at the vicinity of the crack or the vicinity of the notch. Where the stress distribution is non-uniform, the stress is maximum at the tip of the notch. So this is the root radius indicated by rho t. The maximum stress at the tip of the notch, it is given by the expression sigma into 1 plus 2 into c by rho t, where 2c is the crack length. So which can be approximately equal to sigma into 2c by rho t whole to the power of half. So this approach assumes that the theoretical cohesive strength, it has theoretical values, it has reached at the tip of the notch or at the vicinity of the crack or at the vicinity of the notch, while the average tensile stress is at a much lower value. So equating this equation with respect to the previous equation where we got for sigma max is equal to E gamma s by a naught whole to the power of half. So equating these equations, so this is the equation for a notch or a stress which acts as a stress raiser which concentrates the stress at the vicinity of the notch. So equating these two equations, we have, that is sigma 2c by rho t whole to the power of half. Equating these two equations, we can arrive at an equation for sigma, that is the fracture stress required to cause fracture. So which is equal to sigma f is equal to E gamma s, fracture stress is equal to E gamma s into rho t by c a naught whole to the power of 1 by 2. So by inclusion of this term 2 inside, we can have So this is the final equation we have arrived. Sigma F is the fracture stress and E is the Young's modulus, gamma S is the surface energy which has units joules per meter square, rho T is the root radius of this crack, radius at the crack tip, and C is the half of this crack length, where this is 2C is the total crack length, internal crack length, and A naught is the spacing between the atoms in the unstrained conditions. If rho T, if one assumption if we make that the root radius at the crack tip is approximately equal to A naught, then we can have sigma F is equal to E gamma S by 4C whole to the power of half.